Hello, and welcome to this lesson produced by Forge College. We are moving steadily through the Ethereum Fundamentals track, specifically within the Introduction to Ethereum Architecture course. We've reached the module on Ethereum transactions and state changes. In our previous lesson, we focused on practical examples and troubleshooting guides to see how accounts interact in the real world. Today, we're diving into transaction basics and structure. We are going to answer a central question. How does an invisible, decentralized computer network process billions of dollars securely without a central post office or a bank manager checking everyone's ID? If you are new to this, your first look at a raw Ethereum transaction probably felt like staring at an intimidating wall of alphanumeric gibberish. It is perfectly normal to feel a bit lost when looking at long strings of hexadecimal code. To make sense of it, let's use a simple analogy. Think of every Ethereum transaction as a digital shipping package. Attached to the side of that package is a highly detailed, extremely strict manifest that tells the network exactly what to do. You don't need to be a master coder to understand this. By learning to read just 5 specific fields on this manifest, you unlock the ability to see exactly how the network routes value and executes complex instructions. Let's start with the sender. Interestingly, the manifest doesn't actually have an explicit "from" address typed out on it. Your public wallet address isn't written in the code. Instead of a name, the sender applies a cryptographic seal. The network decodes this to recover your address. It's a wax seal only your ring makes. If a bad actor forges your signature, the math breaks and the network immediately rejects the transaction. Next is the nonce, a strict tracking counter. 1, 2, 3. It ensures every transaction has a unique place in line, preventing duplicate replays. If package 4 arrives before package 3, the network holds package 4 in a queue until the missing package arrives. By combining that mathematically derived signature with a strict tracking counter, the network guarantees that nobody can impersonate you, and nobody can process your transactions out of order. Now that we've verified the sender, we need to know where the package is going and what is inside. For this, we look at 3 fields: to, value, and data. On the left, we have a simple native transfer. The to field points to a regular person's address. The value contains some Ethereum, and the data compartment is completely empty. This is like mailing a check. The network just updates account balances. Now look at the right side, a contract call. The to field points to a smart contract gear icon. Value might be 0, but the data compartment is packed with specific blueprints. The network's engine receives these blueprints and executes them, like commanding a standardized digital asset contract to update its internal ledgers to move a token. By simply glancing at whether that data field is empty or full, you can instantly deduce whether a transaction is a simple cash transfer or a complex programmatic work order. But maintaining this global network isn't free. This brings us to gas limits and fees, the postage required to cover the costs of the computers doing the work. Complex blueprints make the package heavier, requiring more gas droplets to balance the scale. This limit acts as a safety fuse against infinite loops. If you don't attach enough gas, processing halts partway with an out-of-gas error. Gas is consumed as payment, but delivery fails. This goes back to our rule on error semantics. Even if the execution fails and the changes are rolled back, the sender still loses their gas fee, and their tracking nonce still increments. This ensures the network is protected from those forever circles, or infinite loops, and that the computer owners are always compensated for the power they expend. When we bring it all together, that intimidating wall of raw transaction code suddenly makes complete logistical sense. Every line of code maps directly to a field on our shipping manifest. Developers and analysts use this knowledge every day to predict how the network will route, charge, and execute a change before it even happens. Now that we can read the labels and route the packages, we're ready for our next lesson: how transactions trigger state changes. We will explore exactly what happens when the network's engine opens those boxes and permanently rewrites the blockchain's history. Thank you for watching this Forge College production. To dive deeper into Ethereum architecture or explore other Web3 topics, please visit our website at forge.college. Remember, treating transactions as mechanical, verifiable shipping manifests is the foundational step to mastering decentralized architecture. See you in the next lesson.